Okay, we're going to talk about chromatic dispersion and how it affects the telecom industry. The basic presentation will start with a definition of chromatic dispersion. We'll do a little bit of mathematics. We'll take a look at two real-life examples, a rainbow and a prism. We're going to look at the sources of chromatic dispersion, and we're going to discuss how chromatic dispersion affects various telecommunication components. All right. So the definition in optics, chromatic dispersion is the phenomena in which the phase velocity of a wave depends on its frequency. Okay, what's that mean? Well, if we talk about a media like like glass or water or air, the speed of light in a media depends on its wavelength. Or another way to say it, the speed of light depends on its color. Now, how much the media slows down the light is measured by the term n. It's called the index of refraction. Typically, the index of refraction decreases as wavelengths increase. If you apply that to the visual spectrum, that means that red will be slowed less than yellow, which will be slowed less than blue. So blue is slowed the most, red is slowed the least. Let's take a look at that when it applies to rainbows. And we look at how the light in a rainbow, the blue is bent more than the yellow, and the yellow is bent more than the red. This is due to the different colors having different indexes of refraction. Now, when we first learned Snell's law, we wrote the indexes of refraction as a constant. Now we know that's not true, but the indexes of refraction are a function of the wavelength of the light or the color of the light. If we do a little math here and make a couple assumptions, we will learn that light of different wavelengths will refract different angles. In fact, the bigger that the index is of refraction, the smaller the angle of refraction. And this here is just the mathematical way of saying that. This means the larger n, larger index of refraction, is going to lead to more bending of light from its original direction. So here we take a look at white light being split by a prism. Now, some of you may be thinking, well, we don't use white light in telecommunication. We use laser light. Laser light will still have a spread of wavelengths that are being used. So chromatic dispersion still will affect single mode fiber. Okay, this is a very nice diagram. And what it shows you is the fact of Snell's law, how the red index of refraction is less. So the angle that it will be deflected from the normal, that's this black line here, is going to be greater than the angle of refraction of violet, because violet has a higher index of refraction. Or if we don't take a look at the normal, we take a look at the direction of light, we see that red is bent less than violet. Violet is bent more. All right, chromatic dispersion, again, it comes from the fact that light travels different speeds based on its color. Uh, Two factors contribute to chromatic dispersion, material dispersion and waveguide dispersion. Dispersion, by the way, is measured in units of picoseconds per nanometer of spectral width. how wide our pulse is in color. And it is measured in terms of per kilometer. So the spread chromatic dispersion gets more and more the farther along the fiber that you travel. All right, material dispersion is used just simply from the fact that different colors of light travel at different speeds. Different wavelengths of light travel at different speeds. So we see how we have a nice narrow pulse before we put it through the fiber, and we have a wider pulse when we put it through the fiber. Notice how the red is slowed less than the purple. The purple is slowed the most, and this expands the pulse length. All right, waveguide dispersion basically says that the longer wavelength is bigger. Well, of course. And so more of it travels in the cladding as opposed to the core of the fiber. Thus, it suffers more dispersion. All right, to correct for dispersion, we produce zero chromatic dispersion. And what that involves is through various devices or various chemical compositions of the fiber, we can get negative dispersion. So we see here how in this fiber, special fiber, the purple is going to travel faster than the red, the inverse of the normal dispersion. So we take this piece of fiber, hook it to a normal piece of fiber, and the two cancel out. Okay, this sounds like a really great idea, but the problem is these zero chromatic dispersion fibers are high cost and have much higher loss. There are other elements that we can use to get zero chromatic dispersion or get the negative so we can have a net zero. One is called a Bragg grating. A Bragg grating here basically says I have the core and at stripes in the core, I am going to use a higher index of refraction than the normal core. This is going to produce uh, negative dispersion. We can use a pair of prisms like we saw. We can use something called a chirped mirror. Basically, the depth of the mirror varies and the composition of the mirror varies so that we get varying degrees, varying slowing depending on the speed length, the wavelength of light. Okay. The elements that we're going to look at are waveguide select couplers, lenses, lasers themselves, and fiber itself. So basically, wave selective couplers. Here is a view of a wave selective coupler. We see how coming in, we have a common port that has light of consisting of different wavelengths. And they each hit a filter and that filters out the appropriate wavelengths. By the way, this will work in reverse. And if we put various colors of light into the waveguide selective coupler, we are going to get a combined output. So the the waveguide selective couplers are used to make muxers. They're used to make demuxers, putting together beams of light, taking apart beams of light into their component parts. It can be used as an optical filter, selecting out only given wavelengths. Um, this negative chromatic dispersion is actually used in the new iridium doped fiber amplifiers. And these fiber amplifiers are used in dense wave division multiplexing. All right, for lenses, We want to get the lenses to focus the light. Well, if the different colors have different index of refractions, the focal point for each color will be different. So what we do is we take the normal lens, that's this lens here on the left, and couple it with another lens that will correct for the chromatic dispersion, i.e. produce negative chromatic dispersion. The two lenses will be made of different materials, and these two lenses together are called an achromatic doublet. All right, lasers are affected by the chromatic dispersion. Basically, if we look at a pulse of light coming down, the index of refraction is going to be higher with a higher wavelength. Higher wavelength is to the right. So our nice square pulse is going to be made into a sawtooth. Sawtooth. So what we do is we add more energy at the higher wavelengths so that when it goes down the fiber, that part is ground down and we're left with a nice square function. This works, chose a square function because it is easy to see the examples. This is equally true when we use a Gaussian distribution of laser light, which is the norm. Okay, the optical dispersion of the laser light, the spreading out in time, actually determines the pulse length of the pulse emitted by the laser, and thus determines the signaling rate. So it's quite substantial. A discussion of dispersion can be, as discussed, the dispersion can be controlled with pair of prisms, diffraction gating, and chirped mirrors. The fiber itself will disperse the signal. So we use some of the correcting mechanisms that we talked about before. And I did want to point out a nifty thing. What is done with many fibers is the end is ground to a lens, like we discussed. And that way, divergent light's diverging here. See the two blue lines going in a different direction, is focused and it's called collimated, going down the fiber. All the lines are parallel. All right, so we learned that the speed of light in a media is dependent on its wavelength. We learned that this leads to chromatic dispersion. We learned that we can correct for chromatic dispersion, and we learned that chromatic dispersion is often the limiting factor in our cable length runs.